Wanted to give a short intro today about inductors. We're just going to talk about what inductance is and what an inductor is, and we'll talk from a very high level on this video. And in other videos, I'll show you how to work out some of the problems and some of the equations behind the behavior of our inductor. So to understand what inductance is, we need to understand two main principles of electromagnetism. Okay, first is if we put a current carrying conductor over a compass, for instance, a magnetic compass, you'll see the needle moves. That's because when we have moving electrons through a wire, it creates a magnetic field. The other principle that you need to know is that when we have a moving magnetic field, for instance, if we're growing a magnetic field or if we're turning a magnetic field, it will induce a voltage or create a voltage. And actually, it'll be counter in the opposite direction of the voltage that created that field in the first place. So those are the two principles that we're going to apply when we talk about inductance, because it helps to understand what that inductor is doing. Okay, so basically, if we have a wire with current flowing through it, we also have these magnetic flux lines in perpendicular to it. What that means is we're creating a magnetic field around the current carrying wire, and if the current is flowing in this direction, you're going to see the magnetic field in that perpendicular direction as well. So in the second drawing, you see here that we've looped the wire. And when we do that, those magnetic flux lines actually line up closer in a circle. And what that does is it creates an actual magnet. So in the left picture, you see an actual permanent magnet with a north pole and a south pole. And in the right picture, you see what we call an electromagnet. This is some kind of core material that we've wrapped a wire around. And you can see as the current flows through that wire, it sets up a magnetic field in that core that looks a lot like the domain of the permanent magnet in the picture on the left. Okay, so inductance, the definition of that is the property of a device that will cause a voltage to be induced, that's where inductance comes from, in response to a change in the current flow. The device that we're talking about is called an inductor, also referred to as a coil, because that's actually what it is. It's a coil of wire wrapped around a core material. Sometimes the core material is air, but it's the coil of wire that we're talking about. That's the inductor. The inductance level determines the strength of the magnetic field in the coil due to that applied current. So if you think about what we could do with that coil that would set up a stronger magnetic field, that would actually increase the inductance of our inductor. And the higher the inductance level, the greater the strength of the magnetic field. So basically, we're talking about a greater inductance means a stronger magnet, okay, for lack of a better term. And the way this happens in our circuit is as we apply a voltage to our circuit and we start to see that current grow, the inductor wants to push back against it initially. It doesn't want to allow that current to flow through the inductor. So it pushes back because as that coil sees that current start to grow through that wire, it creates a magnetic field. And like we said, a moving magnetic field, which you can imagine if the magnetic field starts at zero and it's growing, that's actually a moving magnetic field. It creates a voltage or induces a voltage that is counter to the one that created it. So it's kind of like it's pushing back against the current for initially. I like to think of it kind of as a water wheel, okay? You know how a water wheel works. When we start to allow water to flow, I'm not sure if this video is going to play. Let's see if I can get it to play. As we start to see water come onto that water wheel, it'd be nice if this would play. The water wheel doesn't turn initially, right? it takes some time to overcome that inertia and actually start to turn. And then if you, sorry, this video isn't going to play, I guess, in my setup here. I'll try to post the link to the actual video for you to look at. Anyway, and what happens, most of you are familiar with the water wheel. What happens when you stop that water flowing to that water wheel? Does the water wheel stop immediately? No, it doesn't. And that's kind of how the inductor works. It has that current, that stored energy, so to speak, and it wants to continue that afterwards. So let's move on here. So basically, here's our circuit, and I'm going to go over exactly what I just told you. I'm going to say it one more time, this time with a circuit diagram here. So when we close that switch, the current's going to start to flow through the circuit, but initially the inductor is pushing back against that current, so it's not allowing all that current to flow. And then gradually, and the reason this is happening is because, again, as we're seeing that current start to steadily increase in the coil of wire, it's creating a magnetic field, and that magnetic field, as it grows, is creating a voltage that's pushing back against the original. So, you see this trying to start a current through the coil's pushing back, and then eventually it will allow that current to flow through the circuit. So let me show you some different inductors here, and your book has a lot of good information about different inductors, so you can review that. But you'll see all kinds of different shapes, different configurations of these inductors. And all of them have slightly different magnetic properties, but they're all set up to create a strong magnetic field. So here is a basic inductor, okay, or a coil. And they're designed to set up a strong magnetic field. So what factors influence the inductance value of this inductor? What do you think we can change about the inductor that might make a stronger magnet? Turns out there are a few different properties we can change. First of all, we can change the core material. Air, it turns out it's not all that easy to set up a magnetic field in air. Air is pretty much what we'll compare everything else to. However, if we find some kind of ferromagnetic material such as iron, and we use that as the coil instead, it's much easier to create a magnet out of iron. So we're going to take into account the material. Okay, so when you see this mu character that you remember as micro, when you see the mu, we call that permeability. That's the ability to set up a magnetic field in the core material. Okay, so different materials will have a different permeability. There's not really a table to look at either to determine the permeability relative to that of air. As it turns out, the permeability of a material actually depends upon not only the material characteristics, but also the current that we're applying. So I'll show you later how to determine that, but for now, I'll just give you the permeability there that you'll need. And then a couple other things we can change about this coil. We can change the number of turns. We can have a lot of turns or a small number of turns. And that is in our equation as n squared. Okay, so turns out it's really important, the number of turns. So we square that in the equation. Because if you double the number of turns, you're actually multiplying the inductor value by 4, by a factor of 4. Or if we triple the number of turns, we're multiplying the inductor value by a factor of 9, okay? So it's very important and makes a big difference in our inductor value. The other two properties about this coil that we can change is the cross-sectional area of the coil itself, okay? So how large it is. And then, of course, the length of the coil is another property we can change. So if we increase the permeability or the permeability of the material of the core, or if we increase the number of turns, or if we increase the area of our inductor, we're increasing the inductor value itself. However, if we increase the length, then we're actually decreasing the inductor value because to lengthen it will decrease its ability to set up that strong magnetic field. Okay, so in the next video, I'll show you some of these calculations, and we will work some problems from here.